Today, I wanted to share with you some very recent and exciting progress in our understanding of black holes, in particular to what happens to information that falls into a black hole. This question was first studied by Stephen Hawking back in 1974, who showed that information that falls into a black hole seems to disappear, to be completely lost. This result has been a huge puzzle for the community, I guess now for 45 years. And I think the biggest leap in our understanding of this problem happened within the last 9 months. So it's a very exciting time, and I wanted to share that with you. So the goal of this talk is to explain what the paradox is and to give you a glimpse into the new ideas that seem to resolve it, at least partially. To do this, I have to explain what a black hole is. To explain what a black hole is, I need to introduce Einstein's theory of general relativity. Okay? So around 1915, Einstein was trying to understand what gravity is. And what he was led to was that gravity is, in some sense, it's the curvature of space-time. It's not a force in the usual sense, and that what actually happens is that massive objects bend space so that your motion looks like you're moving. Well, your motion is, it takes you towards that massive object, and therefore it seems like there's a force. So, for example, if you have the Earth, the space-time is bent such that this person here is forced to fall towards the Earth. Said differently, the space-time structure is that the Earth is to your future. This is sort of the refined understanding of what the force of gravity is. In some sense, the theory of this theory of Einstein's theory of general relativity should be thought of as how space-time paths are altered by mass or energy. As we know from Einstein's E equals mc squared, mass is the same as energy. The equation that Einstein proposed that governs how the space-time is bent by mass or energy is the following equation: R equals T. This is called Einstein's field equation. R here represents the curvature of space-time, and T here is the energy or the mass present in that space-time. So what this says is that the energy sources the curvature of space. It bends space-time in a particular way, but also that the bending of space-time creates energy. So it's a very complicated equation. This kind of equation we call a nonlinear equation. See where I am right now. In fact, this equation is so complicated that Einstein thought it can never be solved. Maybe just approximately, but you can never find an exact solution. This was in the sort of November of 1915. Then came Carl Schwarzschild, just 3 months later, in 1916, and found a solution. And to add sort of insult to injury, he found the solution while serving in the German military on the Russian front. In fact, there's a very nice quote by him where he says, let me see if I can find it. Somewhere here. He says, I think he found the solution, and then he sent it to Einstein in a letter. And in that letter he says, "As you can see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." So it's a really, really remarkable person. And so he found the first solution. Let me write it here. The first, we often call it the first non-trivial solution. And it wasn't until the 1960s that people finally understood what that solution was. And it turned out to be a black hole. The first solution of general relativity turned out to be the most important solution of general relativity. And I'm going to try to explain what that solution is. The solution describes something like this. So here I have this spherical object. And there are a few important aspects of it. In the center here, where r is equal to 0, r is like a radial coordinate. It's a distance from the origin. At r equals 0, we have something called the singularity. I'm not going to talk too much about the singularity, but I'll make reference to it later. There's another aspect, which is this outer boundary of this spherical object, which is called the event horizon. It's located at a point which is, I guess, 2 times Newton's constant times the mass of this object. I'll explain what the mass is in a second. This is so again, this is the event horizon. I'm sure many of you have heard of the event horizon. It's the point of no return. It's the one-way gate of a black hole. Before I talk about that more, what I mean by the mass is if you have somebody who's far away from this object, they feel the gravitational field that they feel. It feels like it's it feels like a planet of mass. It's roughly like a planet of mass m. Okay? And so now let me get back to the event horizon. So again, we said it's the one-way gate. If you have any person sort of floating around the black hole, so long as they don't enter or pass the event horizon, then they can choose to escape far away. But if they cross the event horizon, then they are doomed to fall all the way down into the singularity. This is often described as saying that the gravitational force of the black hole is so strong that nothing can escape. I actually sort of find issue with that argument. The right way to describe it is that the structure of space-time inside a black hole is such that the singularity is to your inevitable future. That's how it works. No matter which way you try to go, any step you take will take you closer to the singularity. In fact, as sort of a very cruel cosmic joke, the faster you try to escape, the faster you fall into the singularity. So my advice to you, if you fall into a black hole, just don't struggle, just accept it. Okay. Let me see. So there's a question of how do you form a black hole? The answer is given to us by this formula. The idea is that if you take, so this radius can be thought of as a critical radius. If you take an object of mass m and squeeze it such that it lies within this radius, then it's bound to sort of crunch into that singularity. So all you need to do is take something very big and squash it to this radius, or something below this radius called, and this radius is named after this person, the Schwarzschild Radius. Let me give you some examples to know sort of the extent of how much you need to squash things. Let's take, for example, the Earth. You need to squash the entire Earth down to a radius of 1 centimeter. It's kind of hard. Another example is the sun.
Oh my.
The sun needs to be squashed down to 2 miles. And most importantly, I was taking these from Wikipedia. Most important example, they have like a list of examples and their respective Schwarzschild radii. And one of them, I kid you not, was a Big Mac. And you need to squash the Big Mac down to 10 to the minus 28 meters. Okay. I think that happens in my stomach all the time. But anyways, so this squeezing can actually happen naturally in the context of stars. So in a star, you have this balance of forces. You have the nuclear fusion inside the star pushing everything outwards. And you also have the gravitational pull of everything towards the center. At some point, the stars can run out of fuel. And so then there's no balancing force. And gravity wins, and it just squeezes everything down, and it forms a black hole. Sometimes, depending on the mass of the star. And I mentioned that to say that black holes are real. So we are studying something real, not just a sort of theoretical exercise. And there have been sort of multiple observations of black holes, but you might actually, well, what does it mean to observe a black hole? You can't actually see a black hole. You know, the reason why you see anything is because light reflects off it, and then you capture that light. But light does not reflect off a black hole. And so the only way to see it is to see it sort of indirectly by the effects that it has on its surroundings. There are three examples that I like of observing black holes. One is the famous LIGO experiment, which has seen gravitational waves of black holes that are orbiting each other. Second, there's this remarkable feat of the Event Horizon Telescope, which was able to zoom into a black hole that is at the center of a different galaxy, M87. And there they were able to see how the structure of the black hole, or the event horizon, deforms the light of the hot gas that's around the black hole. The nicest, or the example I like best, is a series of pictures taken of the black hole at the center of our own galaxy. And it's really crazy. So the series of pictures shows something like this. There are a bunch of stars, huge stars, millions of times the size of the sun, and they're all going around something. And you zoom in, and there's nothing there, but they're going around something, and you can estimate how big the thing in the center has to be in order to support all of these stars, to have all of these orbits, and it's a humongous object. If I'm not mistaken, something like billions.
3 million times the mass of the sun.
Okay, 3 million times the mass of the sun. Okay, thank you.
Wikipedia again.
No,
Wikipedia again. There you go. How many Big Macs is that? And had it been a star of that mass, it would shine really, really brightly. But we don't see anything. And so the most reasonable conclusion is that there's a black hole in the center of our galaxy. Okay, I should have said that, please interrupt me if you have any questions. That was my overview of Einstein's theory of general relativity. Next, I'm going to talk about quantum mechanics. This is when the crazy is going to start.
Before you go on kind of the next theme, I have just a little question here.
Yeah.
You take the Earth and it would be shrunk down to a centimeter, okay, you would have a small black hole. What would be the event horizon on that object?
1 centimeter.
That's the event horizon. But the actual mass, in other words, you've described the singularity, which has all the mass accumulated in it. But the event horizon would be generally larger than that, would it not?
Correct. But everything is sort of going towards the singularity.
So the point is that if some object were orbiting around this black hole, a spaceship or whatever, and it decided, we're going to put on the brakes a hair, and then it crosses the threshold of the black hole, but it still has its speed, and the center of gravity and the center of mass of this object are the same. So I would expect, like the moon or any other satellite, to continue to revolve around forever inside the event horizon, but outside of the actual massive object, which is the center of that. And so would something like that be possible, that Captain Picard or whatever would be stuck forever in limbo, never able to leave, but living forever anyway?
So, yes, they can enjoy themselves orbiting each other for some time.
For an arbitrary length of time?
No, not an arbitrary length of time. Everything inside will crash into the singularity at some point. The singularity, you should think of it as, it's not, so I mean, this is kind of a deceptive diagram. The singularity is not a point in space, it's rather a point in time. It's really to the future of everyone. And time just suddenly stops. Yes.
For the stars that get a little too close, do the orbits ever decay? I don't know if Andrea Ghez went into this when she was talking about the orbits of the stars around the black hole, but do we know if that's ever happened, that the orbits decay and they actually go in?
Lars, correct me, but there are examples of stars that are sort of feeding into black holes.
Okay. Yeah, that's correct.
Okay, so
All stars?
No, some stars get tidally disrupted in distant galaxies. We haven't seen that in our galaxy. But in other galaxies, we've seen evidence of stars getting tidally stripped as they get too close to the black hole. Sort of ripped apart.
Any other GR questions?
Yeah, I guess you said that energy and mass is a warpage of space-time. And if mass is also a field, like particles are fields, would a field be a warpage of space-time?
Yeah.
All right, well, that's the answer then, isn't it? All right, so all we have to know is what space-time is.
Okay. So I'm going to transition to quantum mechanics now. This should write it here. So now we're really changing gears. So quantum mechanics was developed mostly between the 1900s, or 1900 and 1925. But really, this was in sort of formulating the theory, but now we use it everywhere. And it was driven by insight from Max Planck, Albert Einstein, and Niels Bohr. And the first sort of complete formulation of the theory was due to Schrödinger and Heisenberg. And Heisenberg worked along with Jordan and I forget the other guy. Born, maybe? Yes. So Schrödinger is famed for his Schrödinger's equation. Heisenberg developed what is called matrix quantum mechanics. And it's a really insane theory. In fact, I remember back in high school. This is when I was first exposed to quantum mechanics. I remember my chemistry teacher. She used to, in one class, she went up to her table and she said, "In this table, there are atoms, and around these atoms there are electrons." that specific electron has a finite probability of being on the moon. I'm like, what is this crazy lady saying? But I hope that what I'm going to tell you now is going to convince you that she wasn't that crazy. Okay, so the punchline of quantum mechanics is that the universe has an inherent randomness to it. And for example, let's sort of compare something from quantum mechanics and something from normal classical physics. Let's think of a coin. Right? So let's think of a coin, which say I place in a box. Inside that box, the coin could be either heads or tails. Nothing crazy about that. So there are only these two possibilities. But in the quantum world, you have something called a quantum coin. At least what I call a quantum coin. And you can actually have both. It's heads and tails. What does that mean? Let me explain. What this means is that it's not that if you sort of open the box, you see it as heads and tails at the same time. But what it means is that if you have many, many, many copies of this quantum coin, identical copies, in some boxes you'll find heads, and in other boxes you'll find tails. The idea is that before you open the box, the coin was in something called a superposition. It is incorrect to say that it was heads or tails prior to opening the box. And let's see. This superposition, so there's, when you open the box or the boxes, there's going to be some fraction of them that are heads and the other fraction being tails. That's for different fractions, that gives you different superpositions. So for example, you can have a fair coin where it is 50% heads and 50% tails. Okay, so you prepare the coin in a superposition, which is given by that. A nice way to represent this is to, I'm going to use some sort of some mathematics, some formulas. So there's some quantum state psi. So quantum state, which characterizes a superposition. So this is psi for one coin, which I will write as 50% heads plus 50% tails. Okay? And you really have many options. You can choose, for example, 75% heads and 25% tails, or say 100% heads and 0% tails. These numbers, these probabilities, are a prediction for what the result of the repeated experiment is going to be. And so what quantum mechanics tells you is that, or rather, it tells you that in reality, the results of measurements are probabilistic. So this theory, let me just write it down, is probabilistic in measurement outcomes. Okay? So you do the experiment many times and you get different answers. There's a quote from a movie I watched like maybe 10 years ago or something. It says, what is it? That the definition of insanity is doing the exact same thing multiple times and expecting different results. I think we just proved that quantum mechanics is insanity. Now, if this makes you uncomfortable, then you're actually in good company, because Einstein found this inherent randomness very, very unsettling. And it prompted his famous quote that God doesn't play dice. In response to this quote, Niels Bohr said, "Don't tell God what to do with his dice, man." And it was actually this discomfort which led Einstein to discover quantum entanglement. Einstein, along with Podolsky and Rosen, what they considered was, say we consider two coins, not just a single coin. And let's write down the quantum state of the two coins. Okay, in the same fashion that we did here. The first thing you do is you list the possibilities. So you can have heads, heads, or tails, tails, or heads, tails, or, this is a hard one, tails, heads. Okay? And you have sort of the freedom to choose the probabilities for these different outcomes as you wish, provided that their sum goes up to 100%. So for example, let's consider a few examples. So, we can take this thing to be 100%. And then we'll have 0, 0, 0. So this means that in the experiments that you do, you'll always find heads for both coins. Or you can make it completely fair, and you can have 25% for each one. Okay? And then it's completely sort of random. But the interesting case that they noticed was, what would happen if I consider 50% for heads and heads plus 50% of tails and tails, and then 0 for everything else? This is really weird. This says that the two coins always agree in their results. So if I have the two boxes, if I open this box and I find heads, then I will definitely also find heads here. If I open this box and I find tails, then the other one is also definitely tails. And this is independent sort of how close these things are together. So I can take this other coin and put it all the way, in a different galaxy. And the results of the measurements are still going to be perfectly correlated. Heads, heads, tails, tails, and so on. Einstein was so disturbed by this, and I think it was this that he called sort of a spooky action at a distance. To him, when he noticed this, to him this was a demonstration that quantum mechanics is in some sense incomplete, or that there's something wrong with it. It was his in-your-face Niels Bohr. Alas, it turned out that quantum entanglement is very, very real, and has been observed countless of times in experiments. In fact, his paper about quantum entanglement is his most cited paper, surpassing relativity by a lot. So thank you, Einstein. Okay, now I'm going to introduce some more mathematical technology.
If they were both heads and you changed the first one to tails, you'd always find the other one to tails?
No.
Okay, so they aren't connected.
Correct.
You know, I mean, they're both heads when they're together, they're separated. Of course, they're both heads when you find them separately. So why is that entangled?
No. So you didn't have to do, well, I'm imagining that you do the experiment after you separate them. Or sorry, you do the measurement after you separate them.
If they're both heads and you separate them, of course they're going to be both heads.
But they were not both heads before doing the measurement. It's in a superposition of heads and tails. Then you take these two boxes, you put one in one galaxy and one in the other galaxy, and then you do the measurement. And then you'll find heads, or tails, and so on.
But you don't know that but you can't say they were both that at the time because of the superposition.
Yeah, exactly. But although you bring up a good point, that so let's say I find heads and heads, and now I take this and I do something to it, it's not going to affect that.
Yeah, well, that's what you really want with entanglement, because now you got, the communication tests are live. It'd be really cool,
If I have time at the end, there are some results that seem to suggest that something like this can happen. But let's leave it until the very end. Yeah. Okay. Okay. Where was I? Yes, I was going to introduce some mathematical technology to represent this entangled state as something like the following. Okay, so two entangled particles or two entangled coins are represented by this line that connects them. There is sort of, in some weird but precise sense, that a pair of entangled particles can be viewed as a single particle that travels backwards and forwards in what is called imaginary time. Okay. And let me see. Okay, at this stage, I want to make a comment about information. What is information in quantum mechanics? So the correct thing to do is to compare the two cases of the two coins and a single coin. So the corresponding picture for a single coin is that you have a single particle that's not entangled to anything else, and we often represent that by something that looks like this. Okay? I'm developing some rules that are going to be useful for me later, and I really want to sort of give you a taste to sort of some of the sort of mathematical manipulations that we perform when studying this problem. Let's label this coin A and this coin B, and let's label this coin also A. Suppose we do measurements on coin A. I'm trying to sort of give you, or to explain why the single coin quantum state is different than the two coin quantum state. Now let's imagine, so I'm fixing to this case where I have 50% entanglement on both. So now if I have a single coin and I do many measurements on it, I have many copies of it, and I do a large number of measurements, I can determine precisely what the quantum state is. Right? If I find that 50% of my coins are heads and 50% of my coins are tails, then I just put 50-50. That's all good. But what about this case? This case. This also tells me that 50% of my coins are going to be heads and 50% are going to be tails. However, there's an ambiguity, because I can give you a different two-coin quantum state that gives the same results for A. For example, I can consider 50% heads, tails, plus 50% tails, heads. These two states give the same results for A. So in some sense, in this entangled state, by looking at just A, you don't have complete information of what the quantum state is. You cannot reconstruct the quantum state. Okay? Okay, so here it says that you need both A and B in order to know what the full quantum state is. Because you need somebody to tell you that if you found heads, then B is also heads. And if you found tails for A, then B is also tails. Then you can pin this down. Okay? And there is the culprit here is the fact that A and B are entangled. There's a mathematical, or pictorial way rather, of checking whether A and B are entangled, and it's by following the following procedure. What you do is you take this quantum state of A and B, and then you double it in this fashion. And now we're trying to see if A is entangled with B. So we want to know what is the entanglement of A. What you do, what the procedure tells you to do, is that you have to connect the two B's by a line. And then draw a horizontal cross-section and count the number of lines that you cross. So in this case, you cross one line, so then you know that the entanglement is equal to 1. Okay? Let's do the same thing for the one coin case. Well, the one coin case, you do something like this. There's nothing else to connect. You draw the horizontal line. You're not cutting anything. So the single coin quantum state, A is not entangled with anything. Okay, so this is a sort of a cartoon for how to check if A is entangled with anything. Okay. Any questions about that? So, perfectly clear, I see.
So, can I ask you a question?
Of course.
So then I'm nowhere near the sciences. I'm a poli-sci major.
Multiple sciences.
So this is really new for me. But, basically, with the quantum entanglement piece, it's just leaning to the premise of probability on all fronts, just leaning toward probability in theory, correct?
Yes.
Okay, thanks.
I've got a question. If you had two coins, or one coin that was spinning, and it's either, when you stop it from spinning, it's either heads or tails. If you have the one going the other direction that's actually spinning the other direction, as soon as you look at this one and that one stops, it will be in the opposite, if they're both spinning at the same speed. So at the time you stop it, the other one will be opposite, no matter when you stop it. If they stop at the same time, they will be the opposite, because they're going like this.
There is an example of quantum entanglement about spinning particles, but it's are you trying to give sort of a dynamical mechanism for why these two things are always going to be the same?
Yeah, because if it's heads here, it's going to be tails there, but that depends on when you stop it. If you stop it when it's heads here, it'll be tails there.
But there's something connecting them? Is that the idea?
They started out, it's the time. I'm presuming that you're looking at them at the same time.
Mm-hmm. Good. So the thing that you're talking about is really classical correlation. In fact, in that case, there are experiments which I haven't really discussed here, which can distinguish between the example that you gave and an example like this. And really, the example you gave is really classical correlation. You've just timed things in just the right way so that they look the same. It's not really a superposition. Okay. The next step in the development of we're still in quantum mechanics. So in fact, in the early 70s, there was a huge development in understanding entanglement, and it was done by let me see where I have that. By Fulling, Davies, and Unruh, which discovered that quantum entanglement is actually really, really important for, am I reading this correctly? For nothing. What I mean by nothing is empty space. Turns out that empty space is actually full of entanglement. What they showed, so this is called, it's this topic of vacuum entanglement. That empty space, like the space in this room, under sort of any partitioning of it. So if we just take a slice of this room, then there are many, many entangled particles straddling this partition or this slice. And they're entangled in just the right way so that empty space feels empty. In some sense, sort of this entanglement, it's like the glue that holds space-time together. Something important is that these particles are not stationary. It's not, they're not just here and they just stay there. They actually move together. So I can represent that by something like this.
Are you saying space-time is quantized, that it's not continuous?
Not quite, but this is one step in understanding that. So here we're imagining space-time as a fixed structure, and we're just studying quantum mechanics on that space-time. And you find that there's all this entanglement which is required for space-time to feel empty, as I said. Okay, I can finally transition to black hole evaporation. So maybe I'll do that here. So this was pioneered by Stephen Hawking in 1974. Who wanted to understand what is the role of quantum mechanics in understanding black holes. I'll just work here. So let's consider the black hole as such. In this black hole, there's a lot of empty space. There's empty space here, empty space here. Don't force me to say anything about the singularity. So in particular, this means that for a partition far away, let's say, there are particles entangled across this partition. And they can be sort of floating away from, or flying away from the black hole. We can consider also a partition inside the black hole. Both of these particles are going to fall into the singularity. But then Hawking said, what about a partitioning at the event horizon? So right here, so you have a particle here, entangled with a particle there. In this case, you can have the situation where this particle wants to go out, and this particle tries to go out, but nevertheless, it is forced to crash into the singularity. The space-time structure of the black hole is such that it sort of it cleaves these two entangled particles apart. See, the surprising thing that he found is that this process of separating these entangled particles leads to black hole evaporation. It makes the black hole get smaller and smaller and smaller until it completely evaporates away. And I'm going to need some room for this. Over here. So here's the black hole again. Let's imagine taking a cross-section of this black hole. So we slice it in this way. So we draw the picture as such. There's a singularity. What Hawking found, is that if you consider this entangled pair, the particle inside the black hole, confusingly enough, has negative energy, has negative mass. So minus m. Let's suppose that the black hole started with some initial mass, capital M. Okay. Moreover, the particle outside has some positive little m. So the process now is that this thing falls down to the singularity, or falls down or up to the singularity. I don't know how to describe down and up. And it reduces the mass of the black hole. Therefore, the black hole is slightly smaller. Let me exaggerate it. So the mass is capital M minus little m. And we have this particle outside that just flies away with some mass plus m. And this particle is entangled with something there. Okay? So this process keeps happening. The black hole gets even smaller. And you have this thing entangled with this thing. Okay? And so on and so forth until the black hole disappears altogether. I guess let's imagine that the black hole disappeared at this point. There's something confusing here, this is the thing that troubled Hawking a lot, which is that by the end of the black hole evaporation, all you're left with is these two particles, but they're entangled with nothing. So what's here? Question mark. And he did a calculation similar to the calculation I was outlining there to compute the entanglement. So he did essentially the copy. Consider the copy like that. He wanted to compute the entanglement of these two outside particles. And so the procedure says they have to connect this thing with these two lines, draw the horizontal line, and you cut two lines. The entanglement is 2. The punchline here, even if you didn't follow this calculation, the punchline is that by the end of the black hole evaporation, you are left with these particles that have entanglement. They're entangled with something, but that something is not there. So remember here, we said that if A is entangled with something, then having A by itself, you don't have complete information. So part of the information has disappeared. Here, you can get access to the information by having B. If your friend has B, then you can reconstruct the entire quantum state. But here, there's nothing. So all you have is A. And so you've lost information. And this is the information paradox. It's a statement that black hole evaporation creates entanglement. Okay. Now, this is actually a huge problem for physics. Information in physics is preserved almost by definition. Since physics is all about predicting the future, right? You tell me about the state of the universe now, I can tell you exactly what it's going to be, in principle, in the future. But this says that you lose some information. Here you can be sort of the sort of glass half full kind of person, which is to say that this is sort of an opportunity, in that there's still something that we don't understand about combining quantum mechanics and gravity together. Here, what Hawking did was sort of a first step in the context of black holes, and you seem to run into a problem. And so I think the right perspective to take is that we should view this as an opportunity and sort of as a guiding, or rather as a guide for possible unified theories of quantum mechanics and gravity. Once you claim you have one, check if it loses information or not in the context of black hole evaporation. Okay, now, see how much time I have, okay. Let me, the next thing I was going to do was I was going to zoom all the way to 2012. Any questions before that time travel?
Mass particle comes from? How did you? It depends on the minus mass particle. There aren't a lot of those around, are there?
So in general relativity, the definition of mass is really, really subtle, and it's not that okay. Let me confuse you more. If you jump into the black hole to capture this particle and do experiments on it, you would think that its mass is positive. But secretly its mass is negative. I'm sorry, but that's just fact.
You better go on, I think.
Yeah.
So wouldn't negative mass be repulsed by the black hole?
Say that again?
Wouldn't negative mass be repulsed rather
No,
than drawn?
no.
It's not an anti-particle.
Can you put a time scale on when the black hole disappears?
Oh, I don't have a number, but it's really, 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 really long. I mean, if you take even a solar mass black hole, it takes much longer than the age of the universe.
Ones that are created in the collider go right away and don't so.
Yeah, those are tiny, right? Those are tiny. Anyways, so I was going to zoom to 2012. This topic I'm going to call the Firewall Paradox. So this is something, well, in 2012, something was happening here at the KITP. There was a long-term program titled Bits, Brains, and Black Holes, where the information paradox was one of the central themes. And really, the KITP did a phenomenal work in bringing all the experts together during that time. And through the exchange of sort of the ideas, trying to understand the information paradox, going through all of the developments in trying to make the problem more precise between 1974 and 2012, it led to a very interesting result, which I was involved in with a fellow graduate student, Jamie Sully, and Donald Maroff of the UCSB faculty, and the late Joseph Polchinski, the KITP, where we were trying to sort of understand which of the principles of black holes should we give up in order to resolve the information paradox. And the thing that we were led to is that you have to break the entanglement. But not anywhere. Break the entanglement at the horizon. But remember, the entanglement was necessary for the horizon to be an empty place. But if you break the entanglement, it is no longer empty. This region is no longer empty, and instead, what happens is that the horizon is replaced by a wall of fire that we called a firewall. The idea is that because you've lost the glue that keeps space-time together, you can't say that the interior is connected to the exterior anymore. Space-time simply ends at where the horizon would have been. If you were to jump in, you get burnt to a crisp at the event horizon, or the location of the event horizon. And as I'm sure you can understand, the community was not very happy with us. This led to sort of a flurry of responses and responses to responses and other conferences and so on. But it was very exciting that it happened here, or it started here at least. Okay, this brings me to the last topic, which is the most recent updates. But before that, are there any questions?
Why do you call that a paradox?
Well, because we can't find a mechanism that actually creates the firewall.
Oh, okay.
We sort of assume that the entanglement is broken, and then we're led to this.
Got it.
That's one way to say it.
Doesn't this bring into question the whole premise of entanglement in the first place?
It's a really good point. So it brings into question. So
your whole argument for entanglement, honestly speaking, sounded sort of like hand waving. And now you come to the conclusion in 2012 that now we would expect this firewall, and that would conflict with the original premise of entanglement. So that suggests to me that this particular conclusion would bring into question or support the doubt that my skepticism about the whole issue of entanglement in the first place.
You're perfectly justified.
You said that that's been proved separately.
You're perfectly justified. So you might say, but hang on, the way that Hawking derived the radiation is by first assuming that there's nothing here. And now I'm saying that there is something there. So the derivation doesn't hold anymore. So do black holes actually evaporate? You can sort of, we've been having these exact conversations.
And forgive me for belaboring a point. When I first asked my question about what happens when a spaceship gets closer and closer to the black hole, and then all of a sudden, in 1 micrometer, it crosses over the threshold, then why would it not keep circling in the area between the event horizon and the singularity? And, you know, I wasn't really satisfied by the answer, but now you propose that such a situation could never occur in the first place, therefore it would require no explanation. Am I wrong?
Except the thing I'm going to tell you next.
Edge of my seat.
It actually seems to say that we don't actually need a firewall. So this is hot off the press. I don't know what the but there's a refined calculation for what the entanglement is, which seems to give us the answer that we desire without having to break this entanglement. I'm going to try to go through that briefly. It's a bit technical. In 2 minutes, okay. Okay, so this thing has to do with a topic called wormholes. Okay, so this is 2019. The idea is to redo Hawking's calculation, but a slightly modified version of it, where instead of taking one black hole, we essentially take this and we square it. Okay? So we have two of this, so something like again, I'm just going to give you a glimpse of sort of what the calculation is. I'm not expecting everyone to understand this, but I have to do this. So here was the black hole. We copied it this way, but now we copied the entire thing this way. So Hawking's calculation is what I outlined before. We want to compute the entanglement of these outside guys. You draw these two lines inside. Okay, and then you draw this horizontal line. And oh, look, you're cutting these vertical lines, and therefore there's entanglement. But what this new story says is that when you do this calculation, you should allow for gravity to respond to the calculation. This might sound weird. What one finds is that what gravity wants to do is to create wormholes between these objects in this way. And these lines that I was drawing vertically, these wormholes redirect them so that the lines go through the wormhole in this fashion. And they connect the two copies that we have. Now this horizontal line doesn't cut anything. And what did it was these redirecting wormholes. And so this tells you that the entanglement is actually 0. So this is sort of just a flavor of the latest updates on this topic. And there's much more to be said here. There is, for example, it seems to preserve this entanglement, and therefore our assumptions that on the outset were justified. And let me sort of end with some concluding remarks. So the complete story of these wormholes has yet to be settled. And thankfully, we have this amazing program here at the KITP titled Gravitational Holography, which again has been really successful in bringing together many of the quantum gravity experts. And there's a feeling in the air that we're on the edge of something really big, and it's really exciting that this place will be the center of that. Thank you.
More questions? Please.
The question that was raised about the black holes and entanglement seemed to kind of put the idea of entanglement in doubt, as if it's somebody's opinion. That's not true. I mean, entanglement is proven and is seen all the time, experimentally.
Indeed.
Of course. So I'm trying to get my head around some of these things. And so you have a superposition principle. Comes right out of quantum mechanics, the Schrödinger equation. And it would seem to me that if some of the notions that you're talking about, that perhaps quantum mechanics may not exist in a black hole, why would you believe the superposition principle to hold true there to begin with?
I would say superpositions continue to, well, quantum mechanics in general continues to apply, but the results that we're finding is that the naive our naive understanding of gravity is what is changing, not quantum mechanics.
Correct. So, but is it conceivable that this change in gravity would in fact not admit a quantum mechanical solution?
Well, I mean, the philosophy of a physicist is trying to, we say that there's a theory of everything. So we know that there's quantum mechanics, and we know that there's gravity. And there should be some unified description of both. And this is one arena where we're forced to sort of face the hard questions, where both of them are equally important, quantum mechanics and gravity. And again, we're trying, still a work in progress. We're trying to understand how these two things play together. That's all I can say.
Graham.
Yeah, great talk, Ahmed. Thank you very much. A bit elementary, but what you've shown here is two of the force of bringing together quantum mechanics and gravity. I think it's fair to say, correct me if you disagree, but what we're looking at here is a kind of virtuoso thought experiment on black holes. No one's ever been anywhere near one of these things, but you're using your brain power to work out the mechanisms that are going on here. What I'm interested in is going back to time 40, 50 years ago when I started out in this business. The question you'd be asking is, when will you be able to actually probe this experimentally? And I just wondered, honestly, do you foresee in your lifetime experimenters, astronomers ever being able to probe these kind of things using telescopes and other experimental methods?
Using the experimental methods you just described, I think the answer is no. However, there's this emerging field which is using what is called holography. So there's this idea that regular quantum systems, things that we might have in the lab, might possibly have a dual description in terms of gravity and black holes and so on and so forth. And so by studying these simple quantum mechanical systems, we might be able to learn something about black holes. Although, I mean, this is sort of, this seems more in reach, even though it is still pretty far away, than the experiments that you discussed. But the jury's out on that one.
All right. 10 years from now, we'll have him come back and tell us what happened.